this is unusual at the time. This is in the old days, 2016, old days of CRISPR. Okay, so making an enormous deletion is up to 725 kilobases. Now that's not going to be, needed for very many genes, but certainly now the technology is being applied. They've gone. I really wasn't kidding. It's 2016 is the old days of CRISPR, as some of you know. I think they're using similar technology to make chromosomal deletions that are deleting multiple genes. They're using them for translocations, for fusion inversions. So, they're doing some unusual things other than what you probably most think about CRISPR being used for, and that's what this point mutation. But the whole point, this is kind of set in motion a whole kind of creating a really good scenario for really good potential for using genome editing for correcting some of the disease symptoms. Okay, so it all has to do with starting with a disease patient, getting fibroblasts, reprogramming them to iPSC cells, like we talked about. Okay, and then making these deletions. Now they had to use 2 guide RNAs because they're 725 kilobases apart. And what they had to be a little bit tricky with is, okay, this is on an X chromosome, so they don't have to worry too much about targeting both alleles, right? But they wouldn't want to have just one guide RNA go into one cell and make a cut at that dystrophin gene, but the second guide RNA not make a cut in that same cell. The second guide RNA might make a cut in another cell and not have the first guide RNA. So they needed to have cells where both cuts were made by the guide RNAs. Okay. And then once they got those, then they simply differentiated these. Now there is a difference. You don't have to know the details of how they differentiated these iPSCs. Okay, so these are the mutant ones that are out of frame. We'll talk about that in a second. And then they corrected the translation reading frame with the deletion. And then in both cases, so they're isogenic, right? Reframed versus out of frame. What does isogenic mean? Yes?
Well, it can differentiate.
Isogenic? No. Anybody else want to try? Isogenic, yes. They're the same genetic background, right? You're taking, say, patient 1 has a mutation. You generate the iPSCs, but then you take those very same cells and correct the mutation. So everything else in the genome are identical between the cells that now have the original out-of-frame deletion and the cells that have the in-frame deletion. So you don't have to worry about if there's another gene that's influencing the phenotype, whether there's modifiers or suppressors. That's what isogenic is. That's a real important term. And that's kind of the beauty of using iPSC cells. Because you can start from wild type, and create a mutation, and you get isogenic, control, mutant. You can start with mutant, correct the mutation, and again, get control and mutant, isogenic. Now, the second ones aren't going to be isogenic to the first, but you can make direct comparisons without having any concern about genetic background. So, but in both cases, then they differentiated to these 2 kinds of skeletal versus cardiac muscle cells. Okay, these are myotubes. You don't have to worry about the terminology and myocytes. Again, you don't have to worry about the terminology. Okay, now this gets back to thinking more about these exons in the translation reading frame. And I've just added in here some of those domains, functional domains, but don't worry too much about them. But again, 79 exons. You might be interested to know there's also 7 different tissue-specific promoters embedded in here too. So there's actually, in addition to all of the splicing, there's 7 different alternative promoter usage in different tissues. So it's a really complicated gene. But this is just telling you again, just another view of, if you're taking different mutations or deletions that are removing or affecting splicing at any of the introns. Remember, we're not showing, this figure doesn't show any of the introns. Just the gap between each of the exons, of course, could be megabase in size, right? Because these are huge introns. But the reading frame for any altered splicing here has to be the same. Or if it's out of frame, once you have the aberrant splicing, you're going to get a dysfunctional protein. Okay. So this is just giving you some examples. Now you won't be, of course, you're not going to be tested on any of these details, but our paper, the assigned paper, worked on 3 different Duchenne's muscular dystrophy mutations. 2 of them were deletions, 1 of them was a duplication. But I just wanted you to be aware of there's a lot of other mutations that have been characterized, both with deletions, both with respect to causing Duchenne's, the severe, and Becker's, the mild. But now take a look at, okay, you can ignore that there's a nonsense mutation here, so because of a substitution. Here's a missense mutation, but remember, these 3 are going to be essentially null, no function. These are going to be partially restored. We call those hypomorphic. They got reduced function, but it's not completely abolished. But also now pay attention to all of these are out of frame. But look at, so the blank space, they're lined up for what's left, the exons that are retained, but the blank space is representing the deletion. So you see how, because of this deletion, now that remember, the deletion breakpoints are within the introns. So I'm not going to draw all of them, obviously, all 79 of them. But let's just say this is exon 1, exon 2, exon 3. You can have a deletion breakpoint there and there that completely removes exon 2, right? So this is what you would have. But once these are spliced together, you would get exon 1 spliced to exon 3. Doesn't even matter what these intron sequences are. But remember, these exons don't have to be in the same reading frame. So what's taking place here is that because of the deletion and then splicing, 47 was spliced directly to 51, but now it's out of frame. And everything else downstream to that because 51 is in a different reading frame. Same thing with 49 and 51. But look at 48, the deletion of exon 48, 47, and 49 are in the same reading frame. So even though it's missing the sequences for exon 48, it's still partially functional. Now, okay, so I forgot to talk. I'm just looking at up to the internal portion. This is not the entire protein. This is just zoomed in exons 41 to 57. Same thing here. Delete exon 50 and 51. Same reading frames, partial function. You can even delete 7 exons, as long as they're in the same reading frame, they're still partial function. Okay, that's telling you something interesting in terms of the disease, right? But is this telling you anything about the function of the protein, in particular these sequences? Is it telling you anything that you can still have partial function at dystrophin even if you're missing 7 exons? What if I told you you could be missing, I think it's, okay, I'll get to that in a minute. There's a Becker's, a mild form of muscular dystrophy that had been identified and characterized in the 80s, I think, that is missing like 60% of the protein because of a huge deletion. Yet it's a mild form. So that's really telling you that, at least there's some partial function just with the N terminus and C terminus of that protein that you can be missing a lot of those spectrum repeats. Now, it's not 100% functioning, right? They still have, these Becker's individuals still have a phenotype, but they live, I think, normal lifespans. They have some muscle weakness. I think they do develop some cardiac symptoms, but there's nothing like Duchenne. Okay, and this in case you're interested, these are the same pig and rabbit knockouts, but now this is just deleting one exon here, but it's out of frame. One exon here, out of frame. Okay. So it's not just the size of the deletion. Now this is a figure I took from another relatively recent review. You won't be assigned to. This is what I was talking about. 2/3 of the spectrum repeats are missing. So this is lining up the exons that are retained. Now this is not showing the exons. These R's represent those repeat sequences, those little ovals on the previous slide. Okay, but you can be missing all of those and have very mild vectors. Really astonishing for protein function, I think, and unusual. But what that did, now again, you're not going to be tested on it, but what that people almost immediately realized the significance of that is that opened up this way of, it gave a clue for how successful initially with gene therapy, right, where you construct a virus that carries a wild type copy of usually the cDNA of the gene that's affected, as long as that virus, can infect the cells that you want it to infect, and you've got the appropriate promoter on the cDNA for your gene, you can use that virus to infect those cells and express the wild type version and correct the function, right? In principle, it should work really nicely. The problem with using gene therapy for the dystrophin gene is the size of the cDNA, the size of the bloody protein. It's bigger than what the viral vectors used for gene therapy can hold. They cannot, the best one, most commonly used, adenovirus-associated virus, AAV, its size limit, these are capsids. These viruses are structured, they're physical structures. They cannot hold DNA any bigger than what they're supposed to. There's a limit. You cannot put a 14 kb cDNA inside AAV. You just physically will not hold it. But because people realized the significance of the mild symptoms, and now this is that same mild vectors deleting all this internal portion, they realized if they just started taking the knowledge of being able to not have a lot of dystrophin and still get a little bit of function, they started constructing micro and mini dystrophin genes that would fit into an AAV vector of less than 5 kb. And you don't have to know what all of these are, but these are all being tested, and they work to a certain extent. They work in cell models. I didn't keep track of which of them have been successful in animal models or even in human trials, but there are human trials going on now with patients with this very same concept. It might not necessarily be these exact mini dystrophins, but that's the power of recognizing from the genetics something really important about the protein. Okay, and then now this is coming back to the dogs. They have a premature termination codon because of a mutation, I think in an intron. Yeah, it's in one of the splice sites. I didn't look to see if it was a 5' or 3' splice site. By the way, this reminds me, you should review, the essential aspects of splicing, right? Splicing is important to this topic. That will be on the study guide. So 5', 3' splice sites of interest. So it's missing exon 7 and then out of frame when this is spliced together. So these are those same dogs. Well, guess what? They use gene therapy. Now, don't worry too much about it. So these R's, this is the mini construct, the mini dystrophin. This is the N-terminus, H1, H3, and H4 are just these hinges that are in the protein. Don't worry too much about those, but you could relate those back to the full figure. Then these are the spectrum repeats, R1, 16, 17, and 24. Instead of having like 24 of them, we've only got 4. This is in at the C-terminus. Don't worry about that. But dogs, those golden retrievers that have that severe dystrophin that's very much like humans in terms terms of symptoms. Like, you don't have to know details of the histology, but the left panels in all three cases are the untreated, and then these are with the gene therapy. So this is from a sick dog. This is from a dog that has a mutation but had gene therapy. Remember the staining I showed you previously for dystrophin? There's a lot of dystrophin protein that's being produced in the course of this gene therapy. Now these are muscle cells as they're stained for H&E. Okay, so this is the normal, so the blue is the nucleotide, the pink is just all the connective tissue fibrosis, so bad, good. This is more staining for fibrosis now, the blue is that's a different stain, the blue is for fibrosis, better, bad. This is not great, but it's still bad. Okay. And then they have ways of measuring muscle force. Okay, and I don't think they have the dogs lifting weights or anything, but they do put a number on this. And they do get, now this is not 100%, right? These are the dogs with muscular dystrophy. These are the dogs agreeing that have the gene therapy. Right? This is not anywhere close to normal control, but somewhere I have a slide that says even restoring 10% of the function to dystrophin will reduce a lot of the symptoms. 10%. That's fantastic. I mean, with other kinds of gene therapy or gene correction, you know, you're probably thinking of, 50, 60, 70, 100% correction in order to get reduced symptoms. But this is really promising for therapy. This is just one more example, just so you know. You can use oligonucleotides, antisense oligos, to block the splice sites and use that for gene therapy. This has not been, in principle, it works, but they did some clinical testing, and unfortunately, even though some of the symptoms of muscular dystrophy were alleviated, the 4 patients that were tested had responses and adverse reactions to the treatment. So I think this is a promising strategy with other diseases, but not this particular one. Okay, so now we're coming back to, this is the graphical abstract. This is just basically saying, now everybody understand the reframed BMD? What does reframed mean? Versus it's out of frame and reframed. What's that referring to? Other than this first row, the people on that side have been kind of quiet. What does out of frame versus reframed mean? Yes?
Well, out of frame mutations are just that disrupt the protein after the misframe mutation, and reframed are supposedly ones that were fixed, not just the entire function of the protein, but just so the splicing is in frame for the
Splicing, not the translation. The reading frame would be restored, and that's where making this bigger deletion comes in. Okay, so this is this is describing the 3 cell lines, and I know the nomenclature is kind of hard to keep track of, but just keep referring back to this table if you need to. The three patients, they just came from this one center, and they just have to be given some unique identifier. And this is telling you the exons that we're doing. So what I added in here, just to help you visualize things a little bit better, is going back to the same representation of the exons as I had before. So this is the deletion. These are the retained exons after splicing of this deletion. So deletion, remove exons 46 to 51. Okay. Now remember, these are all Duchenne's, so severe. But look, this is out of frame. Exon 45 is out of frame with 52. Exon 45 is out of frame with 48. Duplication of exon 50. Not in frame. Could you have a duplication of any of these exons and retain the reading frame? So for example, could you have a duplication of exon 48? Yeah, because they're the same shape. Okay, any time those shapes will fit together, they're in the same reading frame. But all of these are out of frame. Now, this is what you need to understand. It gets a little bit complicated. So remember, these are huge deletions. Okay, So they have to have a guide RNA here. Now, they only use 2 guide RNAs. That's the beauty of this system. Notice that here's a deletion for the 1003. Here's the deletion for 1006, okay? Now, they don't want to, they're not having the guide RNAs go to these introns. They don't want that. They want to have a single pair of guide RNAs that they can use for lots of alleles. They're showing proof of principle here. So this left guide RNA, the target sequence is in intron 44. Same guide RNA for this intron 44. Same 2 guide RNAs for intron 55. Okay. Now pay attention to the little arrows here. There's a pair of PCR primers for one primer. The forward primer is in exon 55. The reverse primer is in intron 55. Just upstream to where the cut is. That's important too. Because remember, if they've got successful targeting, everything from this target site in intron 44 to that target site in intron 55 will be removed. You still got a little bit of, why would they leave a little bit of intron here? This is like a chimeric intron. A little bit of it comes from intron 44 and a little bit there. So the 5' end comes from intron 44. The 3' end comes from intron 55. Is that a problem? Why not? They're going to be spliced out anyway. Again, that's the beauty of this. Same thing with this other allele, right? Entirely different deletion, but also severe DMD. Target with the same pair of targeting guide RNAs, you get the same deletion. Now, if you've got success, remember, they can't control whether a clone of iPSC cells has had just one targeting here at this end and another cell has that targeting. Ideally, they want both targeting events to take place in the same clone, right? That's where they just have to screen through by sequencing and identify. Or, they might have had, PCR. Well, this is where it helped, PCR. Right, so then they just do PCR with this pair of primers, PCR with that pair of primers. Now, if you're wondering why I want this pair of primers, right, that's going to be homologous to sequence here, right at the end of exon 44, and the sequence, the reverse primer is for the very 5' end of 5. How come they don't see a PCR product from here to here in the non-deleted, non-targeted allele? Let me show you the gel, because then it might make more sense. So this is from, these are 2 figures, one figure, but 2 panels from figure 2. This is the same one that I was just showing you, just a little bit smaller. So you could be looking at it right next to here. So pay attention to the, these are the undeleted primers, gel on the left, deleted primers, the gel on the right. So the undeleted PCR primers are these red ones. You're going to get products of 1201 base pairs. That's what these are. Undeleted, these are the parent cells before they did the CRISPR. Undeleted, reframed. They don't have that PCR product, that 1.2 kb PCR product. Because it's deleted. But now this pair, these are the same DNAs, but with the deleted primers. 758. Only present in the reframed ones that have had both targeted cuts. Now go back to this question though. Why aren't we getting any PCR product with these primers, the purple ones, the deleted PCR, on the 2 parent cell lines, 13 and 51? What are the size of the PCR products that anybody who's done PCR, what size are the PCR products? what's the biggest one you've ever heard of?
Isn't it? Oh wait, never mind.
What?
Never mind.
Typically with PCR, you're doing like
Isn't it
maximum of
800?
a KB or maybe 2 KB. Sometimes if you're trying to clone a big fragment or something, you can do some, you wouldn't be doing the Taq polymerase with a PCR. There are special PCR polymerases that will do big ones. None of them will do 530 kilobases. They don't even have to worry about any contamination. I've done a similar kind of PCR. There is just no way that these primers that are 530 kilobases, or even here 670 kilobases apart, are going to be kilobases, they're going to be amplifying anything. So this established that they're reframed. Now, just look at the rest of the things it has to do with, that's the most important thing to understand. They had to establish they were still pluripotent. They did some Sanger sequencing. Sanger sequencing still can be done. Now, the only other things I want you to look at, and I'll have this in the study guide, know why they're using this particular antibody, MyHC, dystro